Okay, with this small video clip, I want to explain you the calculation part, the EMF calculation in DC generator. Most of the time, there will be one question from this section for the exam. Therefore, you have to clearly understand and remember this formula for exam purposes. Um, so, for a DC generator, the induced EMF uh, is going to be calculated here now. The overall induced voltage in a turn, if you take single turn, which is having two conductors, it will be 2 times BLV, because you know in the two conductors, um, the EMF generated will be in the directions that will sum up both, because one is moving down, the other one is moving up on the same magnetic field. So the two EMF generated will be added up, so the total EMF for one turn will be 2 times BLV. BLV we already know, because the EMF generated by a conductor of length L moving in a magnetic flux density B with velocity v will generate BLV amount of EMF. So as there are two conductors, it will generate 2 times BLV. So here the V is the rotating conductor's speed. So normally the rotating things, we are using the angular velocity omega m, which is measured in radians per second. The relationship between the velocity, tangent velocity, and the angular velocity is V equals omega m into r. Therefore, so I hope you understood that. If I explain it little further, say for example, some particle is rotating. Maybe I will change the color here. Rotating on a circle, say at velocity v. So this is what we call the velocity, and if it is rotating around this axis, say at speed of omega just say omega, right, omega m, and if this radius is r, then this v is equals to omega m into r, right? That is what you get here. So instead of v, we can substitute omega mr, then you get 2bl omega into r, right? So that is the EMF generated by a single turn. Now the magnetic flux density in a DC machine will be non-uniform, because for the conductor, for example, if you look at the magnetic flux between two magnetic poles, say these are the two magnetic poles, where this is N and this is S, right? So these are the two magnetic poles, right? then the magnetic flux lines will be going like this, right? uh, Sorry, they are parallel, right? So like this, so you get the magnetic flux lines like this, and then the conductor, when it is here, uh, you have one flux density, but when you are moving towards this place, the perpendicular I mean the flux perpendicular to the velocity is changing. Here it is exactly perpendicular because the velocity is directly upward, but when it comes somewhere here, the velocity will be in this direction, and perpendicular flux, there is no perpendicular flux. So therefore in this area the flux will be less, flux density will be less. Therefore uh, therefore the flux density is changing, right, not uniform. If you take the average magnetic flux density, so you can write B as phi over A. Phi means the flux, total magnetic flux per pole, only one pole, because we are considering the magnetic sorry, the coil turn while it is under one pole, and if the area per pole is A, then it will be phi over A, right? So here A means the cross sectional area that we are considering. So so in this case, say for example, if this is, sorry, if this is the pole that we are talking about, say having some radius r, right, some radius r, uh, then the total flux is going like this, right? Total flux is going like this. So the area is basically this total area here, which is coming under the coil. So in that case, this length, if this radius is r, the length, this length, perimeter length, will be 2 phi r l, right? 2 phi r l, that will be the total perimeter, right? 2 phi r, and then length of the conductor is l, so the area cut by the conductor will be 2 phi r l, the total one, I mean if you take the full circle. But if you have two poles, this will be divided into two, right? Because one pole is this side and the other pole is this side. So the average cross sectional area in that case will be um, uh, 2 phi r l over p, 2 phi r l over p, right? The 2 phi r l is the total area of this surface, and you divided by the number of poles. P is the number of poles. So then you get B equals P phi over 2 phi r l. L is the length of the conductor. So now if you substitute this B value in 2BLV equation, then you get ET equals, instead of B you put this one to 2B into LV, so L will go off and 2 will go off. Therefore you get P phi into E here, but from the previous slide you can take the second equation. Just let me delete this. Seems to be very slow. Yeah, here it is actually 2BL omega r. Instead of B, we are going to put that value. Then 2 and 2 will get cancelled off, L and L will get cancelled off, and then what you get is this B part and the omega R. So that is this part, P phi over phi, R and L will go off, so and omega will come here, so it is P phi omega M over phi. Okay, this is the total induced EMF by a single turn, right? Single turn. The overall armature winding voltage, that means if you multiply this by number of turns, here in my previous presentation that I shared with you, the Z value was given as the total number of turns, but there was a mistake there, so I corrected that. So number of turns here will be Z by 2, because Z is the total number of conductors. So for one turn there are two conductors, no? Therefore number of turns will be Z over 2, right? So number of turns will be Z by 2, and total number of conductors will be Z, right? Therefore if you calculate this for all Z over 2 turns, then EA is equal to Z over 2 times ET, right? Because this we calculated for one single turn. So then if you substitute ET here, you get P phi omega M over 2 phi, because 2 is coming here, and then Z. So P Z phi omega M over 2 phi, right? So right, so now that is the total induced EMF. Actually there should be a 2 there in this case. There is a little mistake again. There should be another 2 here. You can correct it, but the final equation is okay. So and if there are several, say A of these series combinations of turns connected in parallel, that means, you know, in motors there are parallel paths, that in the way that I have explained earlier. If I go back to that slide, just give me a second. If I, where is that? For example, if you go to this slide here, you see there are 4 parallel windings, parallel paths, right? So what we have calculated is the total amount of EMF generated by all coils. So now the induced EMF on the terminals will be actually the total divided by 4, because we have added all these EMF into one figure in this calculation. So therefore we have to divide that EMF by the number of total paths. Sorry, I don't know why this is not working. Right here. Here. So we have to divide that by a. So z et over a, where z is the total number of turns. um, uh, Total number of turns should be z by 2 actually, so there is a little mistake here. Anyway, the e will be z p phi omega m over a phi. So if you take phi omega m out, and then what you get is z p over a phi, that is actually number of conductors into the number of poles divided by number of parallel paths. So it is called armature constant. It's called armature constant. Sorry, p z over a phi is called the armature constant. So, and then into phi is flux per pole, and omega m is the angular velocity of the motor in radians per second. So we can express the same. So this equation is correct, right? There is a problem with this z, but when I check in several books, z is actually number of conductors, not number of turns. So that mistake was there in my previous presentation. So now EA can be calculated as P phi Z n over 60A, where n is the revolutions per minute, omega is the radians per second, n is the revolutions per minute. So the conversion is, if you want to convert radians per second figure into rounds per minute or revolutions per minute, you have to multiply that value by 2 phi over 60. So if you put n here, that you have to put 2 phi over 60. You have to multiply that by 2 phi over 60 as well. So now you get EA equals P5 Zn over 60A, right? So this is the equation that you have to remember for calculations, so you don't have to worry about how this is derived. So finally what is required is this one. P is the number of poles, phi is the flux per pole, Z is the total number of conductors, n is the revolutions per minute, 60A is the number of parallel paths, right? So that you have to remember. And then I have added few more slides, but I am not going to talk about those slides now. And then I come to this slide, the back EMF generated in a motor. What I have included in previous two slides are for these are for basically generators, not for motors, right? You know, when generator is in operation, an EMF will be generated, but there will be no current going through the coil because the output is not connected to any load. But now if you connect a load, what will happen? A current will flow through the load, and the same current will flow through all the armature coils. So but at no load this current is ideally zero, but there will be very small current going through the armature coils. But now as there is a current going through the coils, and when current carrying conductors are moving in a magnetic field, there will be a Lorentz force that will be applied on each conductor. So that force is in a way in opposite direction to the direction of rotation, to oppose the rotation. Therefore that force can be calculated. So that calculation is explained here, but remember there is such scenario in a generator, always there will be a backward direction torque on the armature. So the external force that you apply to rotate the generator or rotate the armature of the generator is converted into electrical energy. So and then only you get current I as the output. So the input power is mechanical, and then you get the output power, which is equal to uh, um, the EMF generated voltage into current going through the load. So that is how the energy conversion process is happening in the uh, generator. And there is one other scenario which I am not going to explain here, that is called the armature reaction. That is again, when current carrying conductors are there, there will be some um, magnetic field formed around them. So if there is no current, this is the normal magnetic flux lines, magnetic field produced by current flowing in the armature conductors. Uh, Normally the magnetic flux was only due to these the permanent magnets, so field magnets on the horizontal direction. But now if there is a current going through the conductors, it will have magnetic flux formed like this. So the field flux and this flux generated due to armature current will now react each other. Therefore the magnetic field in the air field is no more uniform. It will be something like this, right? So this is called the armature reaction. So due to this, actually a lot of changes happening here, especially at the brushes. We normally place the brushes in the neutral zone, where in the normal case neutral zone is somewhere here. So we put the brushes here because at that point there is no EMF generated on the coil, and when the brush is switching from one commutator segment to other commutator segment, the spark will be less. But when the magnetic field is changed like this, at this point also there is a significant magnetic field, so this coil turn is generating some EMF. So at the brush there will be some spark going on. So because the neutral zone is now moved to somewhere here, it was earlier here, but now it is somewhere here, right? So so this is what we call the armature reaction. Actually this is corrected in practical generators by using interpoles. I hope you remember in my first lecture I was talking about these interpoles. They are actually balancing or the neutralizing the armature reaction. So that way you can bring the neutral zone again back to this place. So if you are interested, you can study about the armature reaction further. Right now I come to the motor uh, situation. In motors we are supplying current, and due to that current there will be force, magnetic due to magnetic field there will be a force on conductors, so it is moving, right? And then again for motors, when there is a current on the coil, in the coil, and that coil is moving in a magnetic field, therefore what sorry when the motor is rotating, when the motor is rotating, uh, it's true that there is a current flowing through the coil, but in addition to that, when a conductor is moving on a magnetic field, in a magnetic field, then it will generate some EMF, right? And that EMF is in a way that is opposing the rotation, right? So the causes for the rotation. So rotation is due to external EMF that you are supplying to the motor. So the induced EMF will be in the opposite direction to the supplied EMF. So that is what we call the back EMF, right? So in this slide I am going to explain about the back EMF. This is mainly related to the motors. The concept of back EMF is related to the fact that armature coils that are moving under the effect of force that is due to armature current, the same conductors while moving through a magnetic field have a voltage induced, that is called the EMF, back EMF in them. In other words, while the machine is running as a motor, part of it is still working as a generator, because the coil is moving in a magnetic field, so it is going to act as a generator as well. So it will be inducing an EMF, and this is called the back EMF. So motor, when it is working, it is acting as a generator as well, so this will create a back EMF. The back EMF is opposed to the applied voltage. The back EMF is only present when the motor armature is moving, and if the motor is stopped, then there is no induced EMF. The induced EMF can never be equal to or equal or greater than the applied voltage. So then if you move on to the next slide, it is talking about the torque that is generated by the motor. The torque developed by a DC machine can be determined by summing up the Lorentz forces on all the armature conductors. So the force applied to an individual conductor, we know it is BIL. So I is the current in a single conductor. So the force on a coil, I is the current on the coil. So if force on the coil F is equal to Fc, then it is equal to B times L times IC, where IC equals the total armature current divided by number of parallel paths. So then the torque will be force into the radius Fc into R. So the total torque will be Fc is BLI over IA over A, and torque is Fc into R. So the total torque will be 2 times Tc. Tc is the torque on single conductor, but there are 2 conductors in a coil. So the total torque will be 2 Z times Tc. That means there will be 2 Z times conductors. Then this will be equal to BLI over A. So for BL, we can apply previous value Pz phi over phi A. So then the equation for torque will be K times phi times Ia. K is the armature constant, phi into Ia, which is equal, armature constant is P phi over phi A, sorry, Pz over phi A, and it is equal to Ea Ia over omega m. that is, if you go back to the EA equation, it is P Z phi over phi A into omega m. Therefore, we can write this part as EA over omega m. So we get torque equals EAIA over omega m. So this equation you have to remember. So now if you write the balance equation, EAIA will be equal to KA phi omega m into IA. So this one we can write as KA phi AIA times omega m. So this part is the total torque, and this is the omega m. So this side is like mechanical power that we get from the motor running at omega m speed, and this is the electrical power that we are supplying to the motor, right? So after this slide, at the end of the presentation, you have some examples. So you have to practice these examples. These are actually very easy. If you remember the equations, you have to just substitute the values and get the answers. So I'm not going to explain these things, but you can do that. Only thing that you must know is for wave windings, number of parallel path is always 2, that I have mentioned earlier in my previous presentations. And for lap windings, A equals P, right? Number of parallel paths is equal to number of poles. So those things you have to remember. For wave winding it is 2, right? Parallel paths will be always 2, but for lap winding, number of parallel paths is equal to number of poles. So if you know that and this equation, then you can easily calculate or find the answers for these questions. Okay, with that I finish the first presentation for DC machines. Thank you.